A CIA analyst stares at a satellite photograph of a shipyard where the snow melts before it touches the roof, betraying a thermal signature that defies industrial logic. He is looking at the birth of a weapon that Western doctrine says cannot exist because the cost of building it should bankrupt the nation attempting it. It is the moment when the rational world realizes it is fighting an enemy that does not follow the rules of survival. In the late 1960s, the Cold War was fought as much in the windowless rooms of intelligence agencies as it was on the high seas. The United States and its NATO allies had constructed a mental model of their adversary that was comforting, logical, and fundamentally flawed. Western naval planners believed that the Soviet Union, while ideologically different, was bound by the same laws of physics and economics that governed the West. They assumed that a warship was an investment, a capital asset that needed to be reliable, maintainable, and safe enough to keep its crew alive for a 20-year service life. This assumption was known as mirror imaging, the dangerous habit of projecting your own values onto your enemy. When the first anomalies began to appear in the reconnaissance data regarding a new Soviet submarine program, the Western analysts dismissed them. The data coming out of the Severodvinsk shipyard was baffling. Intelligence reports indicated the construction of massive, hermetically sealed assembly halls. Thermal imaging satellites detected heat signatures that suggested an industrial process requiring immense energy consumption, far beyond standard steel welding. Logistics trackers noted the movement of vast quantities of argon gas and rare earth metals. The data points painted a picture of a submarine that was being built like a spacecraft. If the intelligence was correct, the Soviets were attempting to build a mass-production attack submarine out of titanium. To a Western naval architect, this was insanity. Titanium is lighter and stronger than steel, but it is a nightmare to work with. It costs 10 times as much as high-yield steel. It requires welding in an oxygen-free environment. Building a single research vessel out of titanium was an impressive feat of engineering. Attempting to build an entire class of combat submarines out of it was industrial suicide. It offered marginal tactical gains for an astronomical price. Therefore, the Western analysts concluded the Soviets would not do it. They interpreted the data as deception or perhaps a limited experiment. They could not imagine that the Soviet Union would commit a significant percentage of its naval budget to a weapon that made no economic sense. This was the first intelligent sin of the Alpha-class program. The West saw the evidence correctly, but they drew the wrong conclusion because they were asking the wrong question. They asked, "Does this make sense to us?" instead of asking, "Does this make sense to them?" The Soviet Union did not view the submarine as a capital investment in the same way the United States did. Under the strategic direction of Admiral of the Fleet Sergei Gorshkov, the Soviet Navy was grappling with a terrifying reality. By the late 1960s, the United States Navy had achieved undisputed dominance in the underwater domain. American submarines were quieter, their sonar was superior, and their crews were better trained. In a conventional war of attrition, the Soviet submarine force would be hunted down and destroyed before it could threaten the American aircraft carrier groups that were the primary targets. Gorshkov and the designers at the Malachit Design Bureau realized that they could not catch up to the West by playing the West's game. If they tried to build a conventional steel submarine that was quieter than the American Los Angeles class, they would fail. The technology gap was too wide, so they decided to change the rules of the game. This decision birthed Project 705, known to the West as the Alpha. It was not designed to be a better submarine in the traditional sense. It was designed to be a doctrinal ambush. The Soviet planners stripped away every assumption about what a submarine should be. They stopped caring about silence. They stopped caring about crew comfort. They stopped caring about ease of maintenance or long-term durability. Instead, they focused on a single, terrifying metric: performance. They wanted a vehicle that could move faster than any torpedo, dive deeper than any destroyer's sonar could reach, and accelerate with the violence of a dragster. They wanted an interceptor. The Alpha was not built to patrol the ocean for months, silently tracking enemy shipping. It was built to sit in a harbor, waiting for the alarm. When NATO carrier groups approached the Soviet bastions in the Barents Sea, the Alphas would surge out. They would sprint to the target area at 40 knots, speeds that were previously thought impossible for a submerged vessel. They would attack, unleash a volley of torpedoes, and then use their speed and depth to escape before the enemy could react. Western analysts missed this intent because they were obsessed with sustainability. They looked at the Alpha and saw a maintenance nightmare. They saw a ship that would spend 80% of its life in the repair yard. They saw a crew that would be pushed to the breaking point. To the American mind, a weapon that is broken half the time is a failure, but to the Soviet mind, a weapon that is broken half the time is acceptable if, in the moments it does work, it is unstoppable. Admiral Gorshkov's calculation was rooted in the concept of asymmetric warfare. He knew he could not match NATO hull for hull. He needed a force multiplier. He needed a weapon that inspired fear. The strategic value of the Alpha did not come from its ability to sink ships. It came from its ability to force NATO to change its behavior. If the United States Navy knew that there was a submarine out there that could outrun their torpedoes, they would have to redesign their entire anti-submarine warfare doctrine. They would have to spend billions of dollars developing new weapons, new sensors, and new tactics. They would have to act defensively. The Alpha was a weapon of psychological warfare made of titanium. It was designed to paralyze the enemy commanders with uncertainty. A single Alpha, lurking somewhere in the North Atlantic, could tie down an entire task force. The escort ships would have to stay close to the carrier. The hunter-killer submarines would have to guard the flanks rather than go on the offensive. The mere existence of the Alpha forced the enemy to respect a threat that might not even be operational. This strategic philosophy explains why the Soviets were willing to accept risks that Western navies considered unethical. The design of the Alpha minimized the crew to an unprecedented degree. Traditional submarines carried crews of 100 men or more, providing redundancy for damage control and maintenance. The Alpha carried a crew of roughly 30, all officers. To achieve this, the designers relied on extreme automation. Computers, not men, would fly the ship. Computers would control the reactor. Computers would load the torpedoes. This allowed the hull to be small and streamlined, reducing drag and increasing speed. But it also meant that there was no margin for error. If a fire broke out, or if the automation failed, there were no spare hands to fight the damage. The crew was not there to fix the ship. They were there to die with it if necessary. Western observers looked at this small crew and saw a weakness. They argued that automation was unreliable, that the workload on the officers would be unsustainable. And they were right. But they failed to understand that the Soviets accepted this fragility as the price of performance. In the Soviet calculation, the safety of the crew was secondary to the lethality of the mission. The intelligence failure regarding the Alpha was a failure of imagination. The West could not conceive of a nation that would treat its submarines like ammunition, expensive, volatile, and ultimately expendable. As the 1970s dawned, the first reports of the Alpha's capabilities began to filter back to Washington. Sonar operators in the Norwegian Sea reported contacts moving at speeds that defied physics. They saw depth readings that exceeded the crush depth of their own torpedoes. The initial reaction was disbelief. The data was labeled as anomalous. The contacts were dismissed as sensor glitches. It took years for the reality to sink in. The Soviets had done exactly what the analysts said they wouldn't do. They had built the impossible machine. The realization sent a shockwave through the Pentagon. The comfortable certainty of American naval superiority evaporated. Suddenly, the Atlantic was not a safe highway for NATO reinforcements. It was a contested zone where a titanium shark could outrun the weapons sent to kill it. The Alpha forced the West to confront the fact that their enemy was not just a copy of themselves. The Soviet Union was a distinct strategic entity, willing to trade blood and treasure for a specific kind of advantage. They were playing a different game. This divergence in philosophy is crucial to understanding the Cold War. It wasn't just a competition between capitalism and communism, it was a competition between efficiency and effectiveness. The West sought efficiency, systems that worked reliably over time. The Soviets sought effectiveness, systems that delivered maximum impact at the decisive moment, regardless of the long-term cost. The Alpha-class submarine was the ultimate expression of this Soviet mindset. It was a technological sprint in a marathon. It was brilliant, dangerous, and doomed. But in the moment of its creation, it achieved exactly what Gorshkov intended. It made the West blink. As the construction halls in Severodvinsk hummed with the sound of argon pumps and high-voltage welders, the Soviet Union was locking itself into a path from which there was no return. They were building a fleet of ships that would require a level of support their economy could not sustain. They were building the future of naval warfare, but they were building it on a foundation of sand. The intelligence analysts who had stared at those thermal images in the late 60s had seen the heat, but they hadn't felt the fire. They hadn't realized that the Alpha was not just a threat to NATO, it was a threat to the Soviet Union itself. It was a machine that would consume the very system that created it. The first step had been taken. The decision to use titanium had been made. The logic of asymmetry had won the argument in the Kremlin. Now, the engineers had to deliver. They had to take a metal that hates to be welded and turn it into a pressure hull that could dive to the bottom of the ocean. They had to take a nuclear reactor and make it small enough to fit in a closet. They were about to embark on the most ambitious and reckless engineering project in the history of the sea. The Alpha was coming, and it would bring with it a lesson that would outlast the Cold War. Performance is nothing without endurance. But before that lesson could be learned, the world would have to deal with the shock of the new. The ocean was about to get much faster and much more dangerous. To build a machine that defies the laws of physics, one must first conquer the laws of chemistry. The decision to construct the Alpha-class submarine out of titanium was not merely an engineering choice. It was a declaration of industrial war against the periodic table. In the grand calculus of the Cold War, where nations usually fought for territory or ideology, the Soviet Union found itself fighting a battle against the element known as T-22. The necessity of titanium was dictated by the unforgiving math of the deep ocean. As a submarine descends, the pressure of the water increases by 1 atmosphere for every 10 meters of depth. At the operational depths envisioned for the Alpha, depths approaching and perhaps exceeding 2,000 feet, the water pressure exerts a force of nearly 1,000 pounds per square inch on the hull. A traditional steel hull, even one made of the high-yield alloys used by the United States Navy, faces a critical limitation at these depths. To withstand the crushing force without buckling, steel plating must become incredibly thick. Thick steel is heavy. As the weight of the hull increases, the submarine loses buoyancy. To compensate, the ship must be made larger to displace more water, or the engines must be made more powerful to drive the massive weight through the sea. The Soviet designers at the Malachit Design Bureau were trapped in a spiral of diminishing returns. They wanted a small, agile interceptor, not a lumbering leviathan. They needed a material that possessed the tensile strength of high-grade steel but the weight of aluminum. Titanium was the only answer. It is 45% lighter than steel, yet it retains its structural integrity under immense compression. It is impervious to the corrosive salt of the ocean, meaning a titanium hull could theoretically last forever without rusting. But titanium is a jealous material. It demands a price that no other shipbuilder had ever been willing to pay. The United States had experimented with titanium components and later would build a deeper diving research vessel, the Alvin, using a titanium sphere. But building a small sphere is radically different from building a 300-foot-long pressure hull that must withstand the violence of combat. The primary enemy of titanium construction is not the metal itself, but the air we breathe. At room temperature, titanium is stable, but when heated to the melting point required for welding, it becomes a chemical sponge. It avidly absorbs hydrogen, nitrogen, and, most dangerously, oxygen. If a welder strikes an arc on a titanium plate in the presence of standard atmospheric air, the metal sucks in oxygen molecules. On a microscopic level, these molecules wedge themselves into the crystal lattice of the alloy. As the weld cools, it does not form a flexible, strong bond. It becomes a brittle ceramic. To the naked eye, the weld looks perfect, but under the stress of a deep dive, that brittle seam will shatter like glass. A hull failure at 2,000 feet is not a leak. It is an implosion that occurs faster than the human nervous system can register pain. To solve this, the Soviet Union had to reinvent the shipyard. At the Sevmash facility in Severodvinsk, on the edge of the White Sea, a new kind of industrial cathedral was erected. It was known simply as Shop 50. Shop 50 was not a standard dry dock. It was a hermetically sealed environment, a massive clean room built on the scale of an aircraft hangar. To weld the hull sections of the Alpha, the Soviet engineers could not simply use gas shielding on the torch, a common technique for smaller jobs. The risk of contamination was too high. Instead, they flooded the entire working environment with argon. Argon is a noble gas. It is inert, meaning it does not react with other elements. By displacing the air in the welding chambers with argon, the shipbuilders created an artificial atmosphere where titanium could be melted and fused without absorbing oxygen. The working conditions inside these chambers were surreal. Human beings cannot breathe argon. The welders, the fitters, and the inspectors had to wear heavy, rubberized suits supplied with oxygen through umbilical hoses. They looked less like shipwrights and more like cosmonauts walking on the surface of a hostile planet. They worked in shifts, moving slowly in their bulky suits, surrounded by the eerie green-blue glow of the welding arcs. The silence in the chambers was profound, dampened by the heavy gas in the suits. Communications were handled by radio. Every movement was deliberate. A tear in a suit meant suffocation. A fluctuation in the argon purity meant scrapping a hull section worth millions of rubles. The sheer scale of the logistical effort required to supply Shop 50 was staggering. The Soviet Union had to divert a significant percentage of its national argon production to Severodvinsk. The mining of the titanium ore, the refining of the sponge metal, the rolling of the thick plates, and the transport to the Arctic, it was a supply chain that spanned the entire Eurasian landmass. Western historians and naval analysts such as Norman Polmar have noted that the construction of the Alpha class was less of a shipbuilding program and more of a national moonshot. The resources poured into these 7 submarines could have built a fleet of conventional vessels. The cost was so exorbitant that even within the Soviet Admiralty, voices of dissent began to whisper. There is a famous, perhaps apocryphal, story involving Admiral Sergei Gorshkov, the architect of the modern Soviet Navy. It is said that during a tour of the shipyard, a cynical officer remarked that it would have been cheaper to build the submarines out of solid gold. The nickname stuck. To the sailors and the workers, the Alpha became known as the Golden Fish, but the investment yielded a capability that terrified NATO. The titanium hull provided more than just speed and depth, it provided invisibility. One of the primary methods used by Western maritime patrol aircraft, such as the P-3 Orion, to find submarines is magnetic anomaly detection, or MAD. The Earth is surrounded by a magnetic field. A massive object made of ferrous metal, like a steel submarine, distorts this field locally. A plane flying low over the ocean can detect this distortion, pinpointing the location of the submerged boat even if it is running silent. Titanium is paramagnetic. It does not distort the Earth's magnetic field. To a MAD sensor, the Alpha-class submarine simply did not exist. It was a ghost. An American pilot could fly directly over an Alpha sitting just beneath the surface, and his magnetic instruments would read nothing but empty water. This magnetic invisibility, combined with the ability to dive below the thermal layers that confuse acoustic sonar, meant that the Alpha was arguably the stealthiest submarine in the world, provided it was moving slowly. It forced NATO to rethink its entire airborne anti-submarine strategy. Millions of dollars had to be spent developing new non-acoustic detection methods, largely because of the metal being welded in Shop 50. The titanium hull also offered a unique durability. In the corrosive environment of seawater, steel is a decaying asset. It rusts. It requires constant painting and cathodic protection. A steel submarine hull gets thinner every year it spends in the water. Titanium, by contrast, forms a thin, tough oxide layer that renders it immune to salt corrosion. An Alpha-class hull theoretically had an infinite lifespan. It would not rust. It would not degrade. It was a permanent object, a diamond in the rough ocean. However, the rigidity of the material introduced new, unexpected problems. Titanium is incredibly hard, but it is also incredibly resonant. Steel has a natural dampening quality. It absorbs some vibration. Titanium rings like a bell. The engineers discovered that the internal machinery, the pumps, the turbines, the gears, created vibrations that traveled through the titanium hull with alarming efficiency. The hull acted as a sounding board, amplifying the internal noise and radiating it into the ocean. The Golden Fish was structurally perfect, but acoustically, it was a drum. To counter this, the shipyards had to develop new isolation techniques. They suspended the internal decks on heavy rubber rafts. They coated the exterior of the hull in thick layers of anechoic rubber tiles designed to absorb both enemy sonar pings and the submarine's own radiated noise. It was a constant battle between the nature of the material and the needs of the mission. The construction process was slow and agonizing. The first hull, K-64, took years to complete. The rejection rate for the welds remained a constant headache. Ultrasonic testing would reveal microscopic pores in the metal, tiny bubbles of gas trapped during the fusion process. These flaws, invisible to the eye, were stress risers. Under the immense pressure of the deep ocean, a crack could start at a microscopic pore and unzip the entire hull in milliseconds. When a flaw was found, the section had to be cut out. The edges had to be remachined. The argon atmosphere had to be reestablished. The welders had to suit up again. It was a process of 2 steps forward, 1 step back. But slowly, the shape of the future began to emerge from the argon fog. The hull of the Alpha was beautiful in a purely functional way. It was a perfect teardrop, smooth and unblemished by the rivets and seams that marked older generations of submarines. It looked like something grown rather than built. As the systems were installed, the cramped reality of the design became apparent. The titanium pressure hull was strong, but it was small. To keep the weight down and the speed up, the internal volume was sacrificed. There were no long corridors or spacious mess halls. Every cubic inch was packed with machinery. The crew would live in spaces that resembled the interior of a spacecraft. There was no room for error, and certainly no room for comfort. The human beings who had manned this vessel were almost an afterthought, biological components squeezed into the gaps between the titanium ribs. The launch of the first Alpha was a moment of supreme triumph for the Soviet military-industrial complex. They had done the impossible. They had tamed the most difficult metal on Earth. They had built a ship that could go deeper and faster than anything the Americans possessed. But a hull, no matter how strong, is just a container. It is a shell waiting for a soul. To make the Alpha truly dangerous, to make it the sprinter that doctrine demanded, it needed an engine that matched the ambition of its skin. The titanium forge had done its work. Now, the baton was passed to the nuclear physicists. They had to design a reactor that could fit inside this small, precious jewel box and generate enough power to drive it at 40 knots. And like the metallurgists before them, they would choose a path that was brilliant, revolutionary, and ultimately fatal. The Golden Fish was built. It was a miracle of materials science, but as it sat at the pier, gleaming and gray, it was waiting for a heart that would prove to be even more temperamental than its skin. The heart of the Alpha-class submarine was not a machine in the traditional sense. It was a captured star held inside a metal bottle. To drive a 3,000-ton hull through the water at 45 knots required an energy source of staggering density. A standard pressurized water reactor, the workhorse of the nuclear navy, was too heavy, too bulky, and too slow to respond. It operated on the principles of a steam kettle, safe, reliable, but limited by the physics of expanding water. The Soviet engineers needed something hotter. They needed a propulsion system that could go from a dormant whisper to a screaming roar in minutes. They needed a reactor that was small enough to fit inside the cramped titanium pressure hull, but powerful enough to generate 40,000 horsepower. They found their answer in a technology that the West had abandoned as too dangerous: the liquid metal-cooled reactor. The reactor installed in the Alpha, designated the OK-550 and later the BM-40A, did not use water to cool its uranium core. Instead, it used a eutectic alloy of lead and bismuth. This mixture is a heavy, silvery substance that looks like mercury but behaves very differently. The physics of this choice were seductive. Water boils at 212 degrees Fahrenheit at sea level. To keep water liquid at the temperatures required for a reactor, 500 or 600 degrees, it must be kept under immense pressure, roughly 2,000 pounds per square inch. This requires thick steel piping, massive pumps, and a heavy pressure vessel. Lead-bismuth, however, does not boil until it reaches 3,000 degrees Fahrenheit. This meant the primary cooling loop of the Alpha did not need to be highly pressurized. The pipes could be thinner, the pumps could be smaller, the reactor vessel itself could be lighter. Furthermore, liquid metal is a voracious conductor of heat. It can pull thermal energy out of the fuel rods far faster than water. This allowed the engineers to shrink the reactor core to a fraction of the size of a standard unit. They packed highly enriched uranium into a space barely larger than an oil drum. The result was a power plant with the highest power-to-weight ratio in the history of marine engineering. It was a nuclear Ferrari engine dropped into a go-kart. When the control rods were withdrawn, the temperature of the liquid metal skyrocketed instantly. The heat transfer to the steam generators was immediate. The turbines spun up with a speed that shocked the helm crews, and Alpha could accelerate from a standstill to 40 knots in a matter of minutes, a feat that a standard American submarine would take much longer to achieve. But this incredible performance came with a thermodynamic price tag that would ultimately doom the fleet. Water has a unique safety feature. It stays liquid at room temperature. If a standard reactor shuts down and cools off, the water just sits there. It is benign. Lead-bismuth is different. It is a metal. At room temperature, it is a solid block as hard as a rock. The melting point of the lead-bismuth alloy used in the Alpha was 257 degrees Fahrenheit. This single number, 257 degrees, became the defining obsession of the entire program. It was the line of death for the reactor. If the temperature of the coolant ever dropped below 257 degrees, the liquid metal would begin to crystallize. It would freeze, but it wouldn't freeze like an ice cube in a tray. It would freeze inside the complex labyrinth of pipes, pumps, and heat exchangers. Once the coolant solidified, the reactor was dead. The fuel rods would be locked in a tomb of solid metal. The control rods would be frozen in place. The pumps would seize. There was no way to simply thaw a frozen reactor inside a submarine. The metal expanded as it cooled and contracted, cracking the delicate internal plumbing. A freeze-up was a catastrophic terminal event. This created a terrifying operational requirement. The reactor could never be turned off. For a standard submarine, returning to port means shutting down the plant. The crew goes home, the reactor goes cold, and the ship rests. For an Alpha, returning to port was the beginning of a high-stakes maintenance vigil. The reactor had to be kept hot, 24 hours a day, 7 days a week, forever. Even when the submarine was docked, the liquid metal had to be kept circulating above 257 degrees. This required a constant source of heat. Ideally, the reactor would be run at a low power setting, using its own nuclear fission to keep the metal liquid. But running a nuclear reactor at the pier requires a full watch crew, constant monitoring, and creates safety risks for the naval base. The alternative was to hook the submarine up to a land-based supply of superheated steam. The base would pump steam from a boiler plant on the pier into the submarine's heat exchangers, keeping the liquid metal warm from the outside. This system worked in theory. In practice, it was a nightmare. The naval bases in the Soviet Arctic, Gromyka and Zapannaya Litsa, were bleak, remote outposts. The infrastructure was crumbling. The steam lines running from the shore boilers to the piers were poorly insulated and prone to leaks. In the brutal winters of the Kola Peninsula, where temperatures dropped to 40 degrees below zero, the steam lines often froze or failed. If the shore steam failed, the submarine crew had minutes to react. They had to scramble to start the reactor and bring it up to power before the coolant temperature dropped to the critical freezing point. It was a constant game of Russian roulette with thermodynamics. The liquid metal itself was also a hazard. While it didn't boil, it was highly corrosive at high temperatures. It ate away at the steel piping and the pump impellers. Worse, when lead bismuth is bombarded by neutrons in the reactor core, it transmutes. The bismuth turns into polonium-210. Polonium-210 is one of the most toxic radioactive substances known to man. It is an alpha emitter, deadly if inhaled or ingested. A microscopic leak in the primary cooling loop would release polonium aerosols into the reactor compartment. The Soviet engineers tried to mitigate this. They sealed the reactor compartment and kept it at a lower pressure than the rest of the ship, ensuring that any leaks would stay contained. But leaks happened. The liquid metal, heavy and hot, would find the smallest crack in a weld. When it hit the air, it would oxidize and form a radioactive dust. The first casualty of this technology was the lead ship of the class, K-64. Launched in 1971, K-64 was the pride of the fleet. But in 1972, while the submarine was at sea, a crack developed in the primary cooling loop. The liquid metal leaked out. As the level of coolant dropped, the flow stopped. In a standard reactor, a loss of coolant is a disaster because the core overheats, a meltdown. On the Alpha, the disaster was the opposite. The coolant that remained in the loop stopped moving. It began to cool. The crew watched the temperature gauges plummet. They tried to restart the pumps, but the metal was thickening. It turned to slush, then to stone. The reactor froze solid. The K-64 was towed back to the shipyard. The engineers looked at the problem and realized there was no solution. The entire reactor compartment, the heart of the ship, was a solid block of radioactive lead and uranium. To fix it, they would have to cut the submarine in half. They did exactly that. K-64 was taken to the Zvezdochka shipyard. The titanium hull was sliced open. The frozen reactor compartment was removed and dumped into storage. The ship was split in two, a broken monument to the unforgiving nature of a liquid metal. K-64 never sailed again. It was used for training and then scrapped. This failure should have ended the program. But the Soviet leadership was committed. They believed the issue was manageable with better training and infrastructure. They built 6 more Alphas. The operational life of these ships became a struggle against the freezing point. The crews lived in fear of a scram, an emergency shutdown of the reactor at sea. If the reactor shut down and could not be restarted immediately, the clock started ticking. They had perhaps an hour or two of residual heat before the metal solidified and the ship became a tomb. The liquid metal technology also introduced a strange acoustic problem. The coolant had to be pumped through the core at immense speeds to carry away the heat. The Alpha used massive electromagnetic pumps, which had no moving parts, but also mechanical centrifugal pumps for higher power levels. The flow of the heavy liquid metal through the pipes created a specific resonant noise. It was a low-frequency rumble, distinct from the flow of water, and because the metal was so dense, it transmitted vibration from the machinery directly to the titanium hull with punishing efficiency. The molten heart gave the Alpha its speed, but it also stripped away its stealth. When the captain ordered flank speed and the control rods came out and the liquid metal surged through the veins of the ship, the Alpha became the loudest thing in the ocean. It screamed. American sonar operators described the sound of an Alpha at high speed as a freight train or a jackhammer. The turbulence of the water rushing over the titanium hull at 40 knots was deafening. The Alpha could outrun a torpedo, but it could not hide from one. It announced its presence to every sensor within 100 miles. This created a tactical paradox. To use its greatest advantage, speed, the Alpha had to surrender its greatest defense, silence. It was a glass cannon. It could strike fast, but once it revealed itself, it was vulnerable. The reactor also imposed a psychological burden on the crew. They knew they were shipmates with a monster that never slept. In port, while other submarine crews went home to their families, the Alpha crews had to maintain a constant reactor watch. They monitored the temperature of the liquid metal, obsessing over every degree. The steam lines from the shore became their umbilical cords. If the boiler plant on the pier broke down, which happened frequently, alarms would sound throughout the submarine. Officers would run through the snow to the pier, banging on the doors of the boiler house, demanding steam to save their ship. There were stories of captains bribing the shore utility managers with vodka to ensure their steam pressure remained high. The survival of a billion-ruble warship often depended on a bottle of spirits and the goodwill of a freezing boiler technician. The liquid metal reactor was a triumph of physics and a failure of engineering. It did exactly what the equation said it would do. It produced immense power from a tiny package, but it failed to account for the chaos of the real world. It assumed a perfect supply of steam, perfect maintenance, and perfect pipes. It was a technology that required a perfect world to function, deployed by a nation that was crumbling into imperfection. As the Alpha fleet grew, so did the maintenance nightmare. The specialized facilities required to handle the polonium-contaminated coolant were rare. The knowledge base was limited to a few specialized officers. The golden fish were becoming hangar queens, spending more time tied to the pier, sucking steam from the shore, than they did patrolling the ocean. The molten heart was beating, but it was slowly poisoning the body that carried it. The Soviet Navy had built a fleet of race cars, only to realize they couldn't afford the gas, the tires, or the pit crew to keep them running. And every minute of every day, the liquid metal waited for the temperature to drop just a few degrees so it could turn back into stone. Inside the titanium hull of the Alpha-class submarine, the atmosphere was defined not by the usual claustrophobic humidity of the Soviet Navy, but by a sterile, eerie quiet that felt more like a spacecraft than a warship. To step into the central control post of an Alpha was to step into a future that never quite arrived. In a standard submarine of the era, the control room was a crowded theater of analog chaos, valves turning, hydraulic levers hissing, and a dozen sailors shouting reports over the din of ventilation fans. On the Alpha, the control room was a sanctuary of screens, buttons, and silence. The Soviet designers had bet everything on the concept of the automated crew. They believed that the speed of modern naval warfare had exceeded the reaction time of the human nervous system. If an American rocket torpedo appeared on sonar, a human captain might take 10 seconds to calculate a solution and shout an order. A computer could do it in milliseconds. Therefore, the ship was designed to be flown, not sailed. The helm station did not feature the massive wooden or steel wheels found on older boats. Instead, the helmsman sat in a padded chair in front of a console that looked like it had been ripped from the cockpit of a fighter jet. He steered the 3,000-ton Leviathan with a small aircraft-style yoke. Behind him, the captain sat not on a raised periscope stand but at a tactical console, surrounded by the glowing displays of the Accord combat system. This high-tech environment necessitated a radical change in the human composition of the crew. The Alpha carried approximately 30 men. In the rest of the Soviet Navy, submarines were manned largely by conscripts, young men serving their mandatory 2 or 3 years, often poorly trained and unmotivated. But you could not put a conscript in the pilot's seat of an Alpha. The crew of an Alpha consisted almost entirely of officers and warrant officers. They were the elite of the elite, the golden crew for the golden fish. They were highly educated, technically brilliant, and paid salaries that dwarfed those of their counterparts in the surface fleet. The food on board was legendary. Smoked meats, chocolate, wine, and caviar were standard rations intended to keep morale high in the high-stress environment. But this luxury masked a terrifying operational fragility. 30 men can fly a submarine, but 30 men cannot save it. In a crisis, a fire, a flood, or a battle, a standard submarine relies on defense in depth. If a pipe bursts in the engine room, a damage control party of 10 sailors rushes in to fight the leak. On an Alpha, there was no damage control party. There were no spare hands. If a fire broke out, the automation was supposed to extinguish it. If the automation failed, the few men available had to abandon their stations to fight the blaze, leaving the submarine's brain unattended. The psychological strain on the crew was immense. They knew they were flying a glass cannon. They knew that their ship was faster and deeper than anything else in the ocean, but they also knew that it had zero redundancy. Every man had to be perfect every shift, every day. There was no margin for fatigue. This tension was amplified by the tactical paradox of the Alpha's greatest asset, its speed. The Soviet doctrine of interception relied on the Alpha sprinting from its base to attack NATO carrier groups. In sea trials, the submarine proved it could do exactly that. When the reactor was pushed to full power, the liquid metal surged, the turbines screamed, and the Alpha accelerated with a violence that threw the crew against their restraints. It could hit 42 knots, perhaps even 45 in a short burst. At that speed, the Alpha was essentially immune to existing NATO weapons. The primary anti-submarine weapon of the U.S. Navy was the Mark 48 torpedo. While the Mark 48 was fast, it had a finite range and a specific engagement envelope. If an Alpha detected a torpedo launch at long range, it could simply turn around and outrun it. The torpedo would chase the submarine until its fuel ran out, eventually dropping harmlessly to the bottom of the ocean. There are apocryphal stories in naval circles of American torpedoes chasing Alphas, only to have the submarine accelerate away, leaving the weapon baffled in its wake. For a brief moment in history, the Soviet Union had achieved invulnerability through velocity. But physics demands a trade-off. To move a submarine at 40 knots requires immense energy, and that energy creates immense noise. When an Alpha sprinted, it ceased to be a submarine and became an underwater siren. The flow of water over the hull at those speeds created a chaotic layer of turbulence. The propeller, spinning at maximum RPM, cavitated violently, creating millions of collapsing vacuum bubbles that generated a roar like a continuous explosion. The reactor coolant pumps driving the heavy lead-bismuth mixture hummed with a low-frequency vibration that resonated through the titanium hull. The Alpha didn't just break the silence, it shattered it. To the sonar operators of the NATO surveillance network, an accelerating alpha was not a subtle contact. It was a blinding flare. The SOSUS arrays, the chain of hydrophones on the floor of the Atlantic, could detect an alpha sprinting in the Barents Sea from hundreds of miles away. It lit up the acoustic spectrum. This created a tactical nightmare for the Soviet captains. They had a ship that could outrun anything, but it could hide from nothing. As soon as they used their speed, they gave away their position to every enemy unit in the hemisphere. Western tactics shifted to exploit this. They knew they couldn't catch the Alpha in a stern chase, so they stopped trying to chase it. Instead, they used the Alpha's own noise to vector an aircraft. P-3 Orions and Nimrod maritime patrol planes would drop patterns of sonobuoys ahead of the screaming submarine. They didn't need to be precise. The Alpha was broadcasting its future position with every second of travel. The Americans realized they didn't need a faster submarine to kill an Alpha. They just needed a smarter torpedo. They upgraded the Mark 48 ADCAP advanced capability specifically to deal with the threat, giving it higher speeds and smarter logic. But even before the new weapons arrived, the Alpha's noise was its undoing. A submarine that is detected is a submarine that is targeted. In a war, the Alpha might survive the first torpedo by outrunning it, but it would have revealed itself to the entire enemy fleet. It would be hunted to exhaustion. The glass cannon nature of the ship extended to its sensors. At 40 knots, the Alpha was deaf. The noise of its own passage washed out its sonar arrays. It was flying blind. To hear the enemy, the Alpha had to slow down. To survive the enemy, it had to speed up. It was a binary trap. The crew lived in a state of oscillating terror, creeping silently at 5 knots, straining to hear a pin drop, or sprinting at 40 knots, deaf and screaming, hoping the speed would save them. The combat control room, with its sleek consoles and ergonomic chairs, was designed to make war feel like a video game. But the reality for the officers was a grueling endurance test. The automation was brilliant when it worked, but terrifying when it glitched. There were incidents where the computer system, overwhelmed by conflicting data, would attempt to initiate emergency maneuvers without human input. The ship would suddenly heel over, or dive, or surface, driven by a line of code that had misinterpreted a sensor reading. The crew had to be ready to physically override the brain of the ship at a moment's notice. And always, in the background, was the reactor. The liquid metal coolant required constant management. Even during a tactical engagement, the engineering officer could never take his eyes off the temperature gauges. If the reactor scrammed during a battle, perhaps due to the shock of a nearby depth charge, the ship would lose power. And if it lost power, the coolant would begin to freeze. The crew knew that a dead stick situation in an Alpha was not just a loss of propulsion, it was a race against solidification. They carried auxiliary heating systems, but these were often unreliable. A battle-damaged Alpha that lost its reactor would essentially turn into a statue within hours. This knowledge created a unique culture among the Alpha crews. They were arrogant, proud of their speed and their elite status, but they were also deeply fatalistic. They knew they were riding a prototype into battle. They referred to their ships as machine guns, weapons to be used up and discarded, not homes to be lived in. The NATO analysts who studied the Alpha eventually came to a conclusion that relieved the panic in Washington and London. They realized that while the Alpha was an engineering marvel, it was a strategic failure. The Soviets had built a specialized interceptor for a war that would likely never happen, while sacrificing the stealth and endurance required for the war that was actually happening. The Alpha could not sit off the coast of the United States and launch missiles. It was too loud and had no strategic weapons. It could not track American boomers in the deep Atlantic. It didn't have the range or the quietness. It was a defensive weapon, a goalie designed to rush out and smash an attacking carrier. But as the 1980s progressed, the Soviet Navy began to realize that the cost of keeping these goalies in the game was bankrupting the team. The maintenance requirements of the titanium hull and the liquid metal reactor were colliding with the crumbling reality of the Soviet economy. The golden fish were spending less and less time at sea. They were becoming hangar queens, high-performance machines that sat in the garage because they were too expensive to drive. The crews sat in the comfortable control rooms monitoring the reactors of ships that were tied to the pier, watching the temperature of the Lead-bismuth, waiting for a mission that was becoming increasingly unlikely. The Alpha had proved that a submarine could fly underwater, It had proved that titanium could be tamed, but it had also proved that in the silent war of the deep, noise is death, and complexity is a liability. The fastest submarine in the world was running out of time, not because of enemy action, but because it was too advanced to survive the decline of the empire that built it. The glass cannon was beginning to crack, and the cracks were appearing not in the hull, but in the infrastructure that supported it. By the mid-1980s, the 7 Alpha-class submarines of the Soviet Navy had established a dual reputation. To the NATO admirals reading intelligence reports in Norfolk and Northwood, the Alpha was still the golden fish, a titanium predator that could outrun a torpedo and dive to the bottom of the world. But to the Soviet sailors stationed in the desolate fjords of the Kola Peninsula, the Alpha was something else entirely. It was a hangar queen. In aviation and naval slang, a hangar queen is a high-performance machine that spends most of its life broken, serving as a donor of spare parts for the few units that are actually running. It is a technological diva that demands more care than it provides combat value. For the Project 705 Lira submarines, this status was not a result of crew incompetence or enemy action. It was the inevitable result of a logistical infrastructure that collapsed under the weight of its own ambition. The Soviet Union had succeeded in building the 21st century submarine, but it was forced to maintain it with 19th century tools. The epicenter of this logistical nightmare was Gromyka, a remote and bleak naval base located on the far eastern edge of the Kola Peninsula. Known to the sailors as the City of Flying Dogs because of the ferocious Arctic winds that scoured the treeless landscape, Gromyka was the only facility equipped to handle the liquid metal reactors. It was a secret city, cut off from the rest of the Soviet Union by geography and security protocols. There were no roads and no rail lines leading to Gromyka. Supplies and personnel had to arrive by sea or helicopter. It was here that the Alphas came to die a slow death by maintenance. The primary enemy was the reactor coolant. The lead-bismuth eutectic mixture was brilliant physics, but it was terrible chemistry. Over time, as the hot metal circulated through the loop, it reacted with trace amounts of oxygen and the steel of the piping. This created oxides, microscopic impurities that clumped together to form slag. This slag was the cholesterol of the ship's heart. It accumulated in the narrow channels of the reactor core and the steam generators. As the flow restricted, the efficiency dropped. To keep the reactor running, the coolant had to be constantly filtered and purified. This required specialized equipment and chemical plants that simply did not exist at a standard naval base. Furthermore, the liquid metal was highly radioactive. The transmutation of bismuth into polonium-210 meant that every pipe, every pump, and every valve in the primary loop was a radiological hazard. A mechanic could not simply unbolt a flange to fix a leak. The entire compartment had to be treated as a hot zone. Maintenance that would take a day on a water-cooled submarine took weeks on an Alpha. The crews found themselves trapped in a cycle of preservation. Because the reactors could not be shut down without freezing solid, the submarines that were not on patrol had to be kept on life support. They were tied to the piers at Gromyka, their reactors idling at low power or kept warm by superheated steam pumped from shore. This reliance on shore steam became the Achilles' heel of the fleet. The infrastructure at Gromyka was rotting. The steam pipes running along the piers were poorly insulated and frequently burst in the -40-degree winters. When the steam failed, the submarine crews were forced to scramble to bring their own reactors up to power to prevent the coolant from solidifying. This constant thermal cycling, heating up, cooling down, switching power sources, wreaked havoc on the titanium hulls and the delicate machinery. The golden fish were being worn out not by the enemy, but by the weather and the poverty of their own base. The operational availability of the Alpha fleet plummeted. Of the 7 ships built, rarely were more than 1 or 2 seaworthy at any given time. The rest sat at the pier, rusting above the waterline, their crews serving as glorified boiler watchmen. They were guarding a fire that could never be allowed to go out, inside a ship that wasn't going anywhere. Meanwhile, on the other side of the Iron Curtain, the United States Navy and its NATO allies were watching the Alpha saga with a mixture of alarm and analysis. The initial panic caused by the appearance of a 40-knot submarine had subsided, replaced by a cold, hard look at the strategic implications. The U.S. Navy faced a decision point. They could try to match the Alpha. they could launch a crash program to build their own titanium submarines with liquid metal reactors. They could chase the speed demon. There were factions within the Pentagon that argued for exactly this. Concepts were drawn up for American fast attack submarines that could hit 40 knots. But the cooler heads prevailed. The American admirals realized that the Alpha, for all its brilliance, was a strategic dead end. They recognized the trade-off that the Soviets had made, speed for silence. The Alpha was fast, but it was loud. In the acoustic war of the 1980s, noise was death. A submarine that announced its position was a submarine that would be destroyed before it could launch its weapons. Instead of trying to outrun the Alpha, the West decided to outsmart it. The U.S. Navy doubled down on sensor technology. They developed the AN/BQQ-5 sonar suite and the massive towed arrays, strings of hydrophones miles long that could detect the noisy Alphas from oceanic distances. If you can see the enemy 300 miles away, it doesn't matter if he is faster than you. You can vector an aircraft to drop torpedoes right on top of him. Crucially, the West upgraded its kill mechanisms. The Mark 48 torpedo was redesigned. The new 80 cap, advanced capability variant, was given a larger fuel tank and a smarter guidance system. It could reach speeds of 55 knots or more. It could dive as deep as the Alpha, and it had the logic to anticipate the submarine's evasive maneuvers. The British Royal Navy developed the Spearfish torpedo, a weapon powered by a gas turbine engine that could sprint at 80 knots. Against a weapon like that, even 45 knots was standing still. NATO realized that they didn't need to build a better submarine, they just needed to build a better bullet. By focusing on stealth and sensors, the Los Angeles-class submarines could track an Alpha without ever being detected. The Soviet Sprinter would be running a race against an invisible sniper. This strategic pivot by the West rendered the Alpha obsolete before it was even fully deployed. The Soviet Union had bankrupted itself building a weapon that had a specific tactical advantage, only to find that the enemy had changed the rules of the game so that the advantage no longer mattered. Back in Gremika, the reality of the failure was becoming undeniable. The crews were exhausted. The golden crews of elite officers were burning out, their morale eroded by the endless maintenance and the futility of the mission. They were trained to be underwater fighter pilots, but they ended up being janitors for a radioactive plumbing system. The physical toll on the ships was visible. Titanium does not rust, but the steel components attached to it did. The complex automated systems, deprived of spare parts, began to fail. Captains were forced to override safety protocols just to get the ships to sea for training exercises. There were accidents, coolant leaks occurred, releasing radioactive aerosols into the reactor compartments. Men were exposed. Some ships were contaminated to the point where sections were sealed off. The hangar queens were becoming radioactive queens, dangerous even to their own sailors. The final blow to the program was not military, but economic. As the Soviet Union entered the perestroika era of the late 1980s, the defense budget began to crack. The cost of maintaining the Alpha fleet was astronomical. Every ruble spent keeping a liquid metal reactor warm was a ruble that could not be spent on the new, more conventional submarines like the Akula and Sierra classes. The Soviet naval leadership, finally accepting the reality that the West had not taken the bait, made the hard decision. They stopped fighting for the Alpha. They realized that the future of submarine warfare lay in stealth, not speed. The next generation of Soviet boats would return to steel hulls and pressurized water reactors. They would be slower, but they would be quieter. And most importantly, they could be turned off. The Alpha-class submarines were quietly withdrawn from frontline service. They were not announced as retired, they simply stopped patrolling. They remained at the piers in Gremika, their reactors still humming, their crews still standing watch, but their mission was gone. They became ghost ships in a ghost city. The wind howled through the superstructure of the base. The supply ships came less frequently. The golden fish waited in the freezing water, monuments to a technological gamble that had failed not because the science was wrong, but because the world was too messy to support it. The hangars were full, but the queens were dying. The engineering had outrun the industry, and now the industry was collapsing, leaving the most advanced machines ever built to rot in the dark. The end of the Alpha-class submarine did not come with a final, glorious battle or a ceremonial lowering of the flag. It came with a quiet, bureaucratic whimper in the chaos of the Soviet collapse. By 1990, the experiment was officially over. The Kremlin, facing economic disintegration and a newly thawed relationship with the West, looked at the ledger of the Northern Fleet and made a pragmatic decision. The golden fish were too expensive to feed. One by one, the remaining K-boats of Project 705 were towed to the breaking yards. It was an ignoble end for the fastest machines ever to move through the ocean. These vessels, which had once terrified NATO admirals and forced a billion-dollar redesign of American torpedoes, were now treated as toxic liabilities. They were stripped of their sensitive electronics, their sonars, and their dignity. But the death of the Alpha program was not just a story of subtraction, it was a story of evolution. The Soviet Navy had learned a painful, expensive lesson in the Barents Sea. They realized that the interceptor concept, the idea of a sprinting, noisy submarine, was a strategic dead end. The future did not belong to the fastest ship, it belonged to the quietest. This realization gave birth to the successors of the Alpha, the Project 971 Shchuka B, known to NATO as the Akula, and the Project 945 Barracuda, or Sierra class. The Akula was a return to sanity. It abandoned the liquid metal reactor in favor of a traditional pressurized water system. It abandoned the complex automation for a larger human crew. And crucially, it returned to steel. The Akula was slower than the Alpha, managing only 35 knots, but it was ghostly quiet. It could skulk in the acoustic shadows of the ocean for months, hunting Western submarines on their own terms. The shift from the Alpha to the Akula marked the victory of pragmatism over ambition. The Soviet engineers admitted that they could not beat the laws of thermodynamics or logistics. They accepted that a submarine that works 90% of the time is infinitely superior to a submarine that works 100% of the time, but only for a week. The Alpha had been a Ferrari. The Akula was a tank. And in war, tanks win. However, erasing the Alpha fleet was not as simple as cutting up a steel hull. The titanium shells were valuable and relatively easy to recycle, but the hearts of the ships, the liquid metal reactors, presented a disposal nightmare that haunts the Russian Arctic to this day. A standard nuclear reactor can be defueled by removing the uranium rods, but an Alpha reactor was different. The coolant was a solid block of lead and bismuth laced with highly radioactive polonium-210. You could not simply drain it. To defuel an Alpha, the engineers had to use external heating units to melt the coolant, carefully extract the fuel assemblies, and then flush the system. It was a dangerous, radiologically hot process. The infrastructure at Gromyka, already crumbling, was not up to the task. In the chaos of the 1990s, the funding for proper disposal evaporated. So the Russians improvised. They removed the reactor compartments entire. They sliced the submarines into sections, isolating the central cylinder that contained the lead-bismuth core. These massive cylindrical units, filled with solidified liquid metal and residual radiation, were sealed with concrete and bitumen. They were dragged to long-term storage facilities inside a bay. Today, if you look at satellite imagery of the Kola Peninsula, you can see them. They look like giant, rusted cans lined up in rows on a concrete pad. They are the preserved hearts of the Alphas, cooling slowly in the Arctic air, waiting for a final geological repository that has not yet been built. They are monuments to a technology that was too dangerous to use and too dangerous to throw away. Only one vessel escaped total destruction, though not in a way that preserved its glory. K-373 was used for a time as a training stand, but eventually, parts of the lead ship, K-64 and others were dissected for study. The surviving pieces of the Alpha program are not ships that sail, but museum exhibits and instructional cutaways. In St. Petersburg and Severodvinsk, fragments of the control panels and sections of the titanium hull are displayed. Visitors can touch the metal that cost more than gold. They can look at the fighter jet yokes that steered the submarine. Plaques celebrate the genius of the Malachit Design Bureau and the bravery of the crews. But the plaques do not mention the polonium leaks. They do not mention the freezing reactors or the steam lines that burst in the winter. They do not mention that the fleet spent most of its life tied to a pier because the Soviet Union could not afford to run it. The history of the Alpha is often filtered through a lens of nostalgia for Soviet power. It is remembered as a triumph of science, and in a pure engineering sense, it was. Achieving 45 knots underwater is a feat that no other nation has matched. The automation was decades ahead of its time. Modern Western submarines like the Astute and Virginia classes now use fly-by-wire systems and reduced crews that echo the concepts pioneered on the Alpha. But as a weapon of war, the Alpha was a failure. It failed the most basic test of military engineering, sustainability. A weapon that destroys its own infrastructure is not an asset, it is a liability. The lesson of the Alpha class is a cautionary tale for any nation seduced by the promise of the Wunderwaffe, the wonder weapon. The Soviet Union believed that a single technological breakthrough could negate the strategic advantages of the West. They believed that speed could defeat numbers, and that titanium could defeat economics. They were wrong. The Cold War was not decided by who had the fastest submarine. It was decided by who had the most robust economy, the most reliable logistics, and the most sustainable doctrine. The United States Navy won the underwater war not because they built better Ferraris, but because they built better Toyotas, reliable, effective, and mass-producible. The Los Angeles-class submarines that hunted the Alphas are still in service today, upgraded and effective. The Alphas are scrap metal. The endurance of steel proved superior to the brilliance of titanium. As we look back at the saga of Project 705, we are left with a sense of awe mixed with relief. Awe at the sheer audacity of the engineers who decided to fill a submarine with liquid metal and send it to the bottom of the ocean. Relief that the Cold War never turned hot, because a war involving these volatile, high-speed machines would have been a chaotic, radioactive disaster. The Alpha-class submarine was the Concorde of the ocean, beautiful, fast, and ultimately doomed by its own excess. It was a machine built for a future that never happened by a country that ceased to exist. Today, the ocean is quieter. The scream of the cavitating propellers and the roar of the lead-bismuth pumps are gone. But deep in the storage yards of the Arctic, the Geiger counters still click near the concrete casks. The golden fish is dead, but it has not yet faded away. It remains a radioactive ghost, a silent reminder that there is a limit to how fast and how deep humanity should dare to go. The engineering outran the industry. The ambition outran the reality. And in the end, the ocean reclaimed its silence, leaving the titanium shards of the Soviet dream to rust, or rather not to rust, on the shores of history. The story of the Alpha-class submarine is one of the most compelling chapters in the history of technology, because it forces us to confront the difference between possible and practical. The Soviet engineers proved that it was possible to build a titanium, liquid metal, automated interceptor. They proved the physics worked, but they also proved that just because you can build something doesn't mean you should. The Alpha serves as a mirror to our own modern obsessions with technology. We often look for the game changer, the single invention that will solve our strategic or environmental problems. We seek the magic bullet. The Alpha reminds us that magic bullets are expensive, fragile, and often dangerous to the shooter. True advancement is rarely about extreme performance in a single metric like speed. It is about balance. It is about building systems that fit the humans who operate them and the societies that pay for them. The men who sailed the Alphas, the golden crews, deserve to be remembered not just as warriors but as test pilots. They strapped themselves into experimental reactors and went to the edge of the envelope. They lived with the risk of freezing metal and burning titanium. They did their duty in a machine that was indifferent to their survival. As the last traces of the Alpha program are buried in the nuclear repositories of the North, we bid farewell to the fastest submarine the world has ever seen. We will likely never see its kind again. The era of the titanium sprint is over. The slow, silent watch of the steel boats continues. If this deep dive into the hidden history of the Cold War and the limits of human engineering meant something to you, we'd be honored to have you with us again. Until next time, stay curious and take good care.